Ba, 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 ba. Dun, 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 da, 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 da. Do, 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 da, 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 da. Da, 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 da. All right. All right. All right. All right. Welcome to the stream. It is a very happy stream, very, very, very merry stream. Uh, I'm glad that you are tuning in. If you're tuning in live, thank you so much for uh, everything that's going on. Sorry for being a little late. Had a couple of calls that ran over. A couple of people that got some really exciting stuff that's going on at Alpha. We are, yeah, just getting going. We've got some pretty interesting stuff today that I that want to bring to you guys. And yeah, obviously the wonderful outfit is because this will probably be the last live stream that we do before Christmas, and so yeah, we're gonna celebrate, and I want you to have a very meowy. It says Catmas down there, but yeah, so yeah, we'll be taking a break for a couple of weeks, but hopefully we'll get some information on this one that will absolutely help you out a lot. And I'm gonna go ahead and tell you, it has been a busy week. I don't know about you guys, it has been quite busy, and because of that, I didn't get to prepare quite as much as I normally do for the stream. But we got some really cool stuff. We're talking about some SIP routing, which if you don't know what SIP is, it's an Allen Bradley thing, and so it'll probably, because I like put it in the title of this, I'll probably get like crazy a bunch of stuff. Yeah, so awesome, awesome. We got joining in from Dubai. That is very much not Alabama. And so uh it's awesome. Thank you for joining, everybody, especially those that are joining from overseas. I know, I guess Dubai, this is probably in the evening for you guys, or um yeah, so that's probably 6 or 7 hours ahead here. So yeah, thanks for joining in. Hopefully you've had a good dinner. Oh, Finland. That's even cool. So that's probably about the same, but even colder. So uh yeah, see it's very good sweater. I mean, they're very happy. Everyone is ready for Christmas, ready for that break. Uh it's so uh but yeah. What do we got? I've got to get my chat pulled up on this thing on the studio mode, because the lag between actual and YouTube messes with my brain. All right, let's get chat pulled up here. Yeah, yeah, yeah. There we go. Much better. Now I can like um do all this. So I realized also from the last stream that the music that I talk about doesn't actually get heard. So maybe I'm gonna try to get the music actually playing to where it could be heard today. Um, but also maybe it's not quite as, maybe it won't be as distracting. So add this and turn it up just a little bit, maybe. Not sure. I have like really bad ADD, and so uh, it's kind of hard for me to listen, to have too much going on. All right, get this up maybe a little bit here. All right, maybe that works. I don't know. Maybe that gate will come in. All right. Anyway, we're talking about, the first thing we're going to talk about today is I had a commenter on one of the videos. I have a video that's talking about a SIP client block for a Siemens S7 or 1500 and 1200 PLCs, and um, yeah. So the this SIP this SIP block. If you're not familiar with what SIP, it's um, I can't remember what it actually stands for. Hold on, it's on here. It's on the support page because I'm gonna bring up this support page because I think y'all need to see it. Which, let me get this going over here. Get me off this, and let's start this up. I want to be in bottom right. Yeah, so here is this SIP page, and if you're not familiar with the Siemens support website, it is actually very helpful. Just you got to know the right place to kind of search for it. But a couple of little tricks. If common industrial protocol. See how much I use. Thank you there, Saif. Hopefully I pronounced your name right. But the common industrial protocol is apparently widely used by Alan Bradley. And this little block here, I have a video going through this block in particular, and it actually gets it to where you can access tags on a Rockwell PLC and pull it into your Siemens block using this SIP block. And one thing, if you notice, there's these little entry IDs and a little shortcut on the Siemens support website. If you do a search for those IDs, it'll go directly to this page. And I'm logged in on the support website, but you don't have to be logged in for most of this stuff. But yeah, so I will kind of post these support IDs, and you can just put those into the page. And also a little trick as well, if you have like a document like this that we're going to go through, down at the very bottom, usually the entry ID for that document from Siemens is down at the bottom, and then you can just Control-C, drop that into your search in support website, and it'll bring up this. So but anyway, this SIP client, we're going to talk a little bit about it because it is pretty cool because you can access tags without having access to the Rockwell PLC program. All you need to know is the exact tag name and to have a network path, which that's kind of one of the things that we're talking about, because I had a commenter ask on that video about that SIP block. The way that I am accessing it is I have a project that I used for that video that I have a 1500 PLC, and I am accessing, I think it's like a Control Logics, it's L3 maybe processor. I don't know Alan Bradley stuff that well, but it has the integrated Ethernet port on it, which is apparently not very common. Apparently that's fairly recent thing that they put that integrated Ethernet port in it. So there's a lot of these systems out there that have network cards in them. And the way that I have mine configured in that video will not work with a network card because there's this SIP routing that you have to do. So reason I brought this client block up is there's a little documentation that we're going to be doing here, and it's available on this page. So if you want to like look this up, there's the I guess I could throw this over into chat. This will be the that's the support ID for this page. So if y'all want to pull up this page and follow along, you can. Really cool block. It's not the most easiest thing to get going, but once you do and you kind of get everything set up, all you need to know is a tag name on the PLC. But what I wanted to do was show on our on this a little bit about how to route this data in using this block, because it's a good thing to know that this block is a little limited. It can only have one network transition, but SIP is most definitely not limited to that. And we're gonna kind of show the kind of like how expansive SIP can be, because SIP is a protocol that kind of like the network path, it goes from jumps. And so once it hits a network transition, it kind of strips away a little bit of that control path, and then it forwards the rest of the message on. So it's kind of, you could start off really complex, and then it cuts it off as it goes along. And so the way that I had my block set up, because it was a built-in processor, the control path for it, the communication path, is based off of this example here. Let me see if I can get that a little bit bigger, because that is not big enough. Let's just go to 100, see if that's good. I have this new PDF reader, because the set of drawings that we had for this plant that we're doing right now is so big that it Adobe doesn't like it. It doesn't like loading up like a 50 some odd meg PDF for some reason. But anyway, so I'm getting used to this. But what we have here is a control path for a processor that the port is on the actual Allen Bradley processor, and this is what I'm using in my video. And so the first path for this SIP client block is actually always going to be set to 1, which 1 gets it to the back plane. So it comes in whatever interface, and then it goes to the back plane with this interface 1. So it comes in on here. Oh my gosh, too much. So it comes in on the network, and then the network card strips that away, and it says, okay, where do I need to go? I need to go to, why does it keep doing that? I need to go to 1. And then it strips away that, and then it says, where do I need to go to? And this next thing is the slot number. And in my program, the slot number is 0 because of it's a built-in Ethernet. Well, I had a commenter that was asking if you could do this on an external card, which is apparently really common for like control logic systems. So if that is the case, then you absolutely can do that. You just have to do the same thing. So when it comes in, you just have to point it to whatever slot your PLC is in. So it can come in on this IP, and then it comes into the back plane, and then wherever your processor is going to be this slot number. And the card itself, because it's communicating on the it's communicating on Ethernet, that's the little Ethernet IP or TCP IP IP address. And so it strips away that, goes to the next thing, which in this case 1 is going to be the back plane. And all this is explained really well in this. This brings up a kind of an interesting point. You may or may not be aware that a control panel, a comfort panel, so like a WinCC, a Siemens comfort panel, has built-in drivers to run with an Allen Bradley processor, and it actually uses SIP. And so if you've ever used a comfort panel or Siemens basic panel, comfort panel, or anything of the like, and used an Allen Bradley driver, you've had to set up this communication path. And this is what this is. And so in this SIP block, there's a really good explanation of this whole SIP communication path. And it comes up really well when you are kind of interfacing in with a comfort panel as well. This, what I have pulled up right here, is a very complicated control path. It has multiple jumps. In this one, you're going to your first access point. You have 2 back planes with a control net, interface cards, and all this stuff. And in this path, you are actually jumping through to multiple back planes and then getting to a separate PLC. So in this one, let's just look at this path real quick. I want to zoom in more. Can I do that? Yes, much better. So super complicated control path here. You have your Siemens PLC. It is coming into, why you wouldn't just go into the .22 here and then into the back plane over to the next. Why not? We're going to do this the most complicated way, and we're going to go into the .32 processor. And so it strips away this .32, and then it goes to the back plane. Eventually the hand will it goes into the back plane, signified by the 1. It goes then into slot 6, which in this case is this 0, 1, 2, 3, 4, 5, 6. And so it goes to slot 6. And then from that, it goes into the control net interface which is this X2. So the output of slot 6. And then it's going to go to address 22, which is a control net address. It goes to control net address 22. And then it wants to forward that to X1, which is the back plane. And then slot 1, 0, 1. And then there is our path. Why you would want to do it that way? That's the network path. So in this one, you would be using one processor to get through the back plane, to go across a control net device into another back plane to get to another processor. All that. Now, I will say in this document, it says that the SIP client block cannot support this. You would have to go in and dig into the actual code to be able to encode this client path, because the SIP client block only uses one network transition. So it comes in and it gets forwarded into that first path, which is going to be the back plane. And then you only have access to the slot on the back plane where your processor is. So we're going to hit escape on this. We're going to hit up this. So in mine, the slot 0 is what you would be dealing with to get that to a built-in processor. So it's going to hit the back plane, come right back into slot 0. If your processor was in a different slot, then you would need to change the slot of this. I want to show you something real quick, though. We talked about this, by the way, this project is a fairly large project. There are quite a few HMIs, quite a few different things that we have on this. And I'm going to show you real quick. I believe the connection is still set up on this, unless I deleted it. I didn't check before. Ah, yes, it is. Haha. So here is a Allen Bradley built-in driver connection for a Siemens comfort panel. So this is kind of awesome. Thank you. So joining in from Russia, like, that's awesome. We've got an international crowd today. I love more people coming in and seeing this. And if you're not, right now we're talking about Allen Bradley. Allen Bradley's mostly in the US. So I'll probably do some stuff and get a lot of US views because I'm talking about Allen Bradley today. But we're going to be getting into some Siemens PLC stuff here in a second. But this is the Control Logix, Compact Logix driver built into the comfort panels. So it uses this same SIP concept. And so this SIP client block is kind of piggybacking on this HMI connection that Allen Bradley kind of opens up. And so the reason why we can access the tags through this SIP client block is because Allen Bradley is like, hey, we want to make our HMIs work pretty well. We want to give access to this. So this SIP communication allows this tag access. And so what we have here, if you can kind of see it, is in this driver, If you select the Allen Bradley Ethernet IP driver in your connection on in your comfort panel connections, it brings up this little screen. So your Ethernet, it's going to be on your Ethernet interface, and your station is going to be a CPU type of either a Control Logics or a SLIC. So Control Logics, Compact Logics, or your SLIC or your Micro Logics. So you have that access there, but it's all going to be using this SIP interface that the CIP client block really explained well on this network path. So here you could set up a this communication path. Say for example, you had an old control net system and you're wanting to get access to some tags on a comfort panel, and you have this kind of control net system sitting over in your plant for some reason. This is the SIP communication path that is described here in this document that we talked about. And so here we would actually be able to do this network path. Now, the way this little dialog box works here is that first Ethernet portion there, and then the rest of your communication path, the SIP kind of like jumps where it strips off. That's here, and this one you can absolutely do a very complicated network path like we have right here. So this network path that we have here, you would absolutely be able to do with a comfort panel to get an Ethernet connection through a control net interface, and get over into the backplane like of a legacy Allen Bradley system. So really cool stuff. So you can use these HMIs, the comfort panel. If you're not aware of kind of the features of the comfort panels, they have some pretty powerful technology that's built into them. And a lot of people don't realize, a lot of Allen Bradley users don't realize that you can do this sort of connection and get these features on an Allen Bradley processor by using this built-in Allen Bradley Ethernet IP connection. So, and I want to say there's even a, so there's an Allen Bradley serial driver as well. And so you can see all of these different drivers that you have here, Modicon, Omron, all the different ones. But we're talking about that Ethernet IP link. So enough of the Allen Bradley thing. I think that the SIP connection is really great, but let's be real. You're probably not on this channel looking for Allen Bradley programming advice. And if you are, I'm not that guy. I have very limited Allen Bradley experience. You are probably on this channel looking for some Siemens tips and tricks, and I'm going to close out this project that we have open, and I'm going to bring up our project that we did. We have been kind of working with for the past couple of live streams, and we've kind of been building up some S120 systems, some G120s, some TCPUs, like all sorts of stuff on it. And I want to show you the next little part of our broadcast today, and it is going to be our it's called HMI Direct Access. So a couple of the things that we've been going through the past couple of weeks has been having to do with the Lucid. The channel is definitely growing, and y'all are part of that growth. And so I guess now would be a good time, since we're talking about the channel growing. The best thing that y'all can do, and I think the people that are here liking the videos, liking the streams, and commenting and communicating. The YouTube algorithm loves comments, loves likes, and the more you're commenting and asking questions, the more these videos are getting out there, and the more we can kind of like spread the love of Siemens. So, but what I wanted to talk to about, because we have a couple of things that we've been trying to do in the past couple of streams, doing with free telegrams and accessing drive data and parameters and Lucid. Yes, there are so many jokes revolving around the name of the German company that we love so much. But yes, we've been talking about how to get some data from our drives, and I wanted to show you a little known fact that there is. It's called direct access, and there are drivers that are built into Siemens HMIs. So, and these are basic panels and comfort panels. So all Siemens HMIs have the ability to directly access parameters on a G120 or an S120. And so you don't even need a PLC. I haven't really been talking about this very much, but you can set up screens on your HMI to directly access not just R values. So in like telegrams, you don't have access to parameter values, but this direct parameter access, you can actually go through and set like values that are actual P values. So things like P210, which is like voltages, or settings for your drives. You could set up like motor data. You can do all of that directly from an HMI, no PLC involved. And I want to show you how to do that today. I'll go ahead and swap over, and we have a, let me do this. Left screen. Where do I need to be? I need to be down here? No, it'd be over here. So just like we talked about before, we have these entry IDs, right? So I showed you this trick. We're going to go here. We're going to go to back to our this. We're going to do a Control V. I'm going to bring up this Dynamics GS HMI Direct Access, and I'll throw this over into chat. Remember, this is the Siemens support website entry ID. So you can just go to support website, type that into, or copy that into the search Site Explorer search box, and it will directly pull up this this page. And I'm showing you today the documentation that's available for download here. The HMI Direktzugriff. Yeah. Any German speakers in here? That HMI Direct. That's what I think it says, because it is HMI Direct Access. So I'm going to step through this because we're going to go through and we set up it is an S7 connection. So let's go back into our, my pointer's like jumping between the two screens and it's really messing with me. So let's go through, and we don't have an HMI in any of these. So let's set up an HMI. And for this, I'm going to just do a basic panel, because alpha, we like to use our these S7, or sorry, basic panel, 7-inch basic panel. So we're going to go here, and 7-inch for our simple systems, we're going to use that, and we're going to throw in that the GB, I believe that's it. Yep. Yeah, this the GB has the Profinet, and we're going to toss that here. Toss a coin to your witcher and let it spin. Don't be impatient. Don't be impatient. We're going to call this our basic HMI. And there's a reason I'm putting it on this one, because I'm going to access some values on this, these G120s here. So we're going to save this, and I'm going to click this because I'm going to scribble this down. So we're a 6802. I'm just writing this down because I don't remember anything that I don't write down. 0, 2 is our, and we're going to access some values on that. So we're also, for the time being, so we're going to pull up our HMI. We're going to go to connections. And we are going to add a new connection. We're going to call this our master drive. I would say type F in chat for you master drive people. Oh, it's such a great drive. Memories. But what we're going to use is we're going to use our SIMATIC S7 300/400 connection, and we are going to Profinet interface on this. What was that, 4? Yeah, 4. And this one we are going to point to our drive, which is on 2, and check to make sure we're doing everything right. Oh, this is a Profibus. Why would you do it Profibus? Here we go. So the Ethernet of your HMI, and then for the control, that slot 2 slick operation expansion are not relevant, because the reason the expansion slots in the racks are not relevant is because this is kind of doing some back-end shenanigans in order to make this happen. And so the trick is, once you set up that connection like we have here, it's really all you need. And we're just going to create a tag now called what parameter do y'all want to get? I know we need R89, right? We're definitely wanting to read that, I think, and that is phase voltage U, and then we're gonna do, and this is actually a real value, and we're going to talk about that here in a second, but we're going to do U, V, W, and sad face on these. Here, U, V, W. Okay, and so our connection is going to be on our master drive connection. Master drive connection for all of them. And our address is how we're actually going to get access. That's all we need, is just our address. And so go ahead and save that. And so how do we define this address? First of all, let's go through and open up this drive master and get the parameter, because I want to show you parameter 89 specifically, because it has parameter view, probably extended parameters, and 89. Oh no. Was it 89 that we were wanting? We were wanting phase voltage. Maybe it wasn't 89. Or is it just that we are going to... we won't do that right now. We totally had this before. Oh, it might not be on. Hold up. Is this only available on S120? Have we done this? Have we made this way? Is that what we're looking at here? Because 89 is actually only on. Yup. There's our problem. So, all right, real quick. You know this is live, and this is real world stuff. R89 is only available on an S120 apparently. It's not available on this, so let's do this real quick. No one will know the difference. Oh, that's probably... Is that going to delete the whole thing? Okay, no. No one knows the difference. 024. Yeah, and this will actually give us a little bit better. Now, cool thing about it is same stuff works because we are still in this, but we were wanting to do 89, and I realized that it got quiet all of a sudden because the music died. Okay, so we still want to do this UVW. Now, doing this on an S120, it does make it a little bit more complex, but not too much. And if you don't appreciate the fact that because this is all in a single portal project, I was able to do what I just did, and that this would actually be okay. Like, if you don't appreciate that fact, like, oh, bless your heart. It's Portal can be cool sometimes when it's not eating up like 32 gig of memory and crashing your computer. But no. So we've got this actual phase voltage that we're looking here. And let's look at this documentation here. Because what we're going to do is we're going to be pointing to a specific parameter based on how we make this address. Okay, so the basics is the data block number is going to be your parameter number. Okay, and then there's a little bit of a thing for the data block, like the actual DBD value. For us, it's going to be DBD because this is a real value, just like we have here in the motor temperature that they're pulling through here. So we're going to go ahead and say this, that I'm going to pull this down on another screen. And for our for this, so our DB value is going to be DB 89. For all three of these, because it is parameter 89 and then it has an index. So parameter 89 for all three. 89 for all three. And then now let's go back to this and let's figure out what this parameter index is. Now, because this is on an S120, we may need to. Well, in the compilation, this connection. So the question was whether or not the connection needed to be updated because we changed networks. So the thing about this connection is when we do this compile, this is the interface for the HMI, and this is the interface for the drive. And as long as this address here is .2 is the same for the drive, then there's no problem. So normally you would absolutely have to have gone and done that, but it just so happened to be that the master drive has the same IP address as the S120 system. So the HMI doesn't know a difference, and because this is in a portal project, the HMI can be shifted around in between all of that. So great question, Steve. If this was, say for example, on the same network, and this was like a .7, we would absolutely have to go back in and update this to a .7. But it just so happens, by happenstance or by luck, the IP addresses were the same for both controllers. So great question. So back to this. So one thing about the difference, the reason I was going to do this for the G120 was because the G120 technically has drive object numbers, but it's just the same for everything. An S120, because it is one drive system to rule all drive systems, it has so many different options of drive kind of objects. And so if you're not familiar with what a drive object is we go into the device view of our S120. There's actually a lot of stuff underneath that one point, and that is a highly technical term. It's a lot of stuff. And hit Control 5, pop up our inspector window here, and I want to show, if I click on this, it brings up all of our stuff. And where does it show it? There, it talks about drive object numbers in here. So this is in, if you were looking for the drive object number in starter. And so drive object numbers are each, you can kind of think about it, if something has a expert list, so it has a parameter list, it's going to have a drive object number. Control unit, terminal blocks, motor modules, CB boards, like anything that has a expert list or a parameter set has a drive object number. Here's how you find them in the Dynamics. It's just in the configuration telegram, or the telegram configuration. It tells you the drive object number. So hopefully portal is kind of the same place. It's probably the slot number if I had to guess. Let's see, does that change? Oh no, I need to stop clicking. Nope. Where is it? So let's see if we can find, this goes back to me not being prepared. Ah, there they are, item numbers. It's kind of the same place. What are you talking about? See, I knew where that was. What are y'all saying? So drive object numbers. So these item numbers in your Telegram configuration is your drive object number. And so for this, we're working with our lead axis. And so we have a drive object number of 2. In a G120, this would always be 1. And the reason why this is important is because in our documentation, our actual, so you have data block number and then actual word number. In this case, because it's a real value, we have to do a DBD, so a double word. But our actual data value is not straightforward. So our drive block offset, our data block offset, which is that DBD, is 1024 times drive object number plus your index number. So how about let's do this? Because I want to go through this, and let me get my stuff pulled up here and start it up so I can draw. Has anybody in chat actually ever used these functions while I'm getting this up? We've got a couple of people here today, so if you've used this direct parameter access, let me know in chat, because I don't think many people know about it. but it's one of the coolest things that you can do. So, is this gonna work? Yes. All right, so let's flip over to our page, our sketch pad down here, because I want to go through this. Yeah, most I have not found many people that, so our DB is 1024 times drive object number. So on a G120, this were a G120, this would always be 1024 because your drive object number on a G120 is always 1. So your DO is always 1. That on a G120, but on an S120, that is not the case. So on ours, our drive object number is 2 in this case. So we are at 2048 plus parameter index. So for our first value, so for R89 index 0, this would be plus 0. So our index 1 would be plus 1, and then index 2 would be plus 2. Straightforward. So we go back up to our we go back up to here. Let me not block this off. Go back up to our tag connection. This is going to be DBD 2048 plus 0. 2048. We are engineered. So it's going to be 2048 plus 1. That's it. Like, for real, that's it. And so now we could actually go through, and now another thing, we can set our acquisition cycles. If you notice, we can get these pretty quick. We can go through and acquire them pretty fast. So let's say fairly fast, and you can actually set up faster ones of these. I don't think you can set up much faster on the basic panel. But this is an HMI video. We're drives people. We'll do an HMI. We'll do an HMI thing another time. But you can speed these up. So 100 milliseconds right now on this basic panel is probably about as fast as we're going to be able to do. But let's make a screen, and let's just do some quick let's do this. Drive. Okay. And then we want some outputs. That's terrible. Undo. Undelete. I wanted to do click here and then yeah, definitely check out some of the other videos. I have some kind of basic videos about kind of like your first steps. Why is this not letting me move? All right, but yeah, for right now, this is kind of a little bit advanced. This is some kind of drive topics, I guess. But for right now, we're getting some basic PLC or HMI setup stuff. So what we're doing right now is we're just setting up this. I'm going to set up this tag. So we click here in our inspector window, and then actually before we do that, let's do this. Control CV, line that up, and then V. Oh, look at that. So fun. So then now let's just drag this over here. Actually get it in the box. Drag V. Click. Drag V. So that's UVW. And so that will, on a 100 millisecond cycle, set up our drive. So that's that R value that, remember, could not be connected via BICO. So we couldn't bring it back over our Telegram in our fast update cycle. But using acyclic communication, which this is using, we got these values. Now, this is coming into a HMI, and this is using HMI Direct. And before we get off this, I want to show you, just put some stuff into your minds about the drives. So Control 5, drop that down. So your parameter 300s are all your motor values, right? And if you notice, all of these are kind of locked. And the reason why these are locked is because they're only accessible when you have a certain parameter value, which in Siemens world, I'm clicking a bunch of stuff. And I know I have some like FA guys from Siemens USA yelling at me because I'm only doing this in expert list and parameters, and you're making it seem more complicated. Well, this isn't straightforward. We wouldn't, if you don't know what you're doing with drives, you probably don't want to be doing this. So, but one of the things of like these values that are like your motor parameter numbers. So like, let's see, rated motor voltage. It's got this little lock on it. That lock is because this is not in a commissioning state. And so what we can do is if we go up here to P10 and we set it to motor commissioning, should give us the ability to change some of these. Actually, well, maybe it's the fact that it's not on. Well, anyway, something's locking that out. Just in the parameter list for right now, and it's not really the point. But if you wanted to change some of these values online, for example, this drive commissioning parameter, this P10, if it is set to ready, there are some values that you cannot change parameters for. And now with BICO, you can't change any parameter because it's not a BICO, it's a P value. So like these P values here, unless it has this BICO connector, you can't connect something into it. So these P values here, you can't change that value through a Telegram. But with acyclic communication, you could totally 100% go through and use our HMI direct access and set up a screen to where you could go through and set up motor values. But if you wanted to set up motor values, you would need to put the motor or the drive into the this P10. It would need to go into motor commissioning. So on our little screen here, we would want to have, instead of an input only, we would want to have this as a, did I pull that? We would want to set this up as an input output and then set up a tag for parameter 10 and do the same thing. So that way we could change P10 to 4. And then if we wanted to really even go, we could even go as far and do a text list. And instead of using an output, we could go and do this type of stuff here. This isn't quite HMI. Wanted to talk about acyclic communication. And this is an example of it. You are directly accessing an acyclic block. And so let's go down, and I'm going to show you how to do that in your program now. And I just realized that I may not have this library loaded in here. I wonder if we do. I don't think I do. I think I might need to load up. No, it doesn't look like it. Because what I am wanting to do, I'm not going to be there anyway. So we're going to bring up in our, we had our function block or our function call that we made for gearing functions last week. We just need to pull up a, so we can get access to our library. Maybe it's our instructions. That's what we are needing. Optional packages, dynamics. Yes, we do. Haha. The stream can continue. Everybody can cheer my lack of being set up. So we're going to talk about an acyclic block. And let's go ahead and make our own little block for this. Let's add a new block called parameter access. We're gonna do this little function block here. Don't care about all that. We're gonna make this new one. And we're gonna close out everything but that. Because what we are going to use is a little block called assign a parameter. And so we want to use assign a parameter. And let's do, we're going to do this to a G1. Well, yeah, if we want to do that, we need to do it on the other. Because I think the assign a parameter S specifically has a drive object number. So this little block, yeah. So the way it works is access number. Yeah, it's a little bit different. So the difference between these two, pretty simple. Let's do like a G. So just in the same way that we went through and accessed that parameter directly, you can use this assign a parameter S and assign a parameter block to actually get access to your parameters. So on yeah, this is a little, so this, let's just talk about this, because assign a para is the one that is the kind of the best for what we're doing here. Except I'm realizing I probably want to do this on the G120, but we could just do this here. So read write, start is going to be like your execute, and so like a toggle to actually do this. You might want to put this as just whenever, but maybe not. So one thing that we're going to talk about, I guess, here in a second as well, is going to be this PID block. So let's do this. Let's because this little start, sometimes you don't want to access things just all the time. You want to update things at a certain amount of time. And there's a couple of ways to do this. You can go through and add in like a what's it called, a timer block, to where you're doing a timer for every 100 milliseconds or so and timing out and updating that block. Or you can use a cyclic interrupt block. And so let's go through and set up this on our basic system, because I want to use this Sinapera on this. Sorry for swapping back and forth between our two systems. We're going to add a new block, and I'm going to show you about a cyclic interrupt block, and we're going to do our drive access, and we're going to do an organizational block. We're going to do a cyclic interrupt, and we're going to set the cycle time to be 100 milliseconds. And the difference between OB1 and this block, OB30, is that OB1 is just cycles however fast it can, but it has the lowest interrupt. So everything else in the system can interrupt OB1. Whereas this block, every 100 milliseconds, it's going to jump out of OB1 and execute this block, whatever's in here, and it's going to start it. So this might not be the best way to do this, but I just wanted to show you the OB1 block, the cyclic interrupt block, because we're going to use that for the PID here in a second as well. So we're going to use this drive access. It's going to open that up. We're going to pull in our Sinapera block into this one. Now inside of this, bleeding access. In this one, we would just be able to do like a not no op, because I apparently don't have that constant defined. Anyway, so we could run this all the time. So this would be like we could do an always on bit for this. Like we could do that as like an always on. If we wanted to define that tag, we could just set it as M0. And if we wanted that to actually always be on, we could go here. Not that one. Go here in our PLC tags. And we would have to set that. We could do this. This is what I like to do. I like to do no op, data type, Boolean, value, false. And then now that's why I did that before, because I normally always define that. And so the reason we can do this is anytime this comes in, you know it's been 100 milliseconds. Because this cyclic interrupt block is only firing every 100 milliseconds. So you can start this and run this as often as possible. And for this one, read write, does this have in version 17? I don't think it has them. Read write is whether or not it is function block. Okay, so 0 is read, 1 is write. So if you're just wanting to read this R value, we'll just leave it at 0. Parameter number is, I believe that parameter number, sorry, see, I'm looking at the actual number of parameters. Interesting. Yeah, so the number of parameters you're reading. Okay, so you can read up to 16 parameters. I got that one backwards. And so this input value on on that on this here, for the input interface, hardware ID. Yep. So using this block, the hardware ID is going to be the hardware ID of your actual device. And so I believe, yeah, follower Profinet, and it's going to be, make sure that it is your module access, I believe. It's not the Telegram, it is the module access point. And if I'm wrong on that, I'll have to like look it up again. I have a program that I could probably find that actually use this. And then yeah, the parameter itself, there's a document. Let's see if I can find the document real quick on assign a parameter on the Siemens support website. Let's see. All right. They're not a just for downloads. I love the support forum. Usually you go to the support forum and then someone is asked kind of that same question, and then they send you to the actual one. Yeah, so here is the documentation. And the reason I'm bringing this up is because the description of the block, I should have had this already pulled up, but sorry, I did not. Assign a parameter. So let's look at this. So the input is what we're looking at, the parameter structure, because this is what we're needing. Because just like in that direct access, there is a little bit of a structure that you have to what's going on here. Parameter number index value. So there is a value here for this that was not quite as intuitive that we should talk about here. So not quite as simple, and maybe we're kind of getting off in the weeds on this and kind of losing our momentum here. But what we are talking about is this parameter value that is the last input. So the first 5 inputs are fairly simple. The axis number, drive object number in a multi-axis system. So the hardware ID, let's go back to this. So to make sure I'm explaining, hardware ID and axis number. Axis number for a G120 is 1. Axis number for an S120 is that drive object number that we talked about before. Parameter number in this case would be 89. That we're, or sorry, no, it would not be 89. It would be 1, because we're only pulling, actually, we're wanting to pull 3 parameters, 89 index 0, 1, and 2. And this parameter value is the tricky thing that kind of gets you, that can get you hung up. And that's what I'm kind of like, because that's not here. This parameter value, the data structure of the SX parameter. So, yeah, we probably need to go through and like look at, because this is it. So you have, I wish I could zoom in a little bit more on that. Parameter number, index value. So you have this structure that you have to kind of adhere to. And it's has all of the things that you're wanting. Why is it so complicated? Not exactly sure. I feel like there's a another library that streamlines this even better, because this is not quite as difficult. I don't remember it being this quite difficult. So we can come back to this, but this is the block here. Let me bring up this again, and the support entry ID for sign a parameter. We'll see. Put this over here in the chat. And so those are the different ones. So there's a L-axis control library that has this. There is no longer file with start drive. Oh, interesting. I'm just reading this stuff here because once again it has been updated, so that you don't have to go through all of this stuff. Apparently there's another value. So let's go through and kind of work through now. Let's go through and kind of change gears, because we're about an hour into it, and I was wanting to talk about the PID functions, and kind of go through, clear up some of this. I'll have to go through and clean up this project a little bit, but yeah. So Sinapara is the way that you can access acyclically another parameter. And so this parameter data block that we have here, there's a little bit of structure complexity there that you need to pass it, because this is going to be something that is your data repository. So that is your data block where everything's going to be updated into, and that's what this complexity is. So if you're wanting to use sign a parameter, maybe we'll go through and I'll do a little bit more research and get a little bit more detail on that, so I can be a little bit more prepared. I apologize for that on that one. Now, the block, I think the block that I used actually had a wrapper around this. I think it was like L drive control. So, but anyway, I use this sign a pause and the sign a speed a good bit on, if you're using a sign a pause would be a Siemens 111 telegram, which is ePause, if you're familiar with that. And the sign a speed is just a telegram 1, or anything that has a standard control word and then a second set point word for speed control. So these two are really quick and easy to get set up. Sign a parameter, this little data block structure has some to be desired. So let's jump real quick then to go to, we're wanting to do a PID. So let's this, and then let's add new block. Actually, let's go through, and not gonna lie, like, once again, this is something that I have set up before. There's a couple of ways of doing it, and I wanted to show you the technology object way of doing this, this PLC or PID, because you have in your technology object, you have a PID, and you have a couple of different options. You have this PID compact, which technically is not what you would think about a technology object. The technology object is just an like an interface into setting up another block. And I think it says here, so yeah, so the description of this says the technology object PID compact provides a universal PID controller with integrated tuning. It corresponds to the instance data block of the PID compact instruction. The data block must be transferred when you call the PID compact instruction. The PID compact includes all settings for this control root. So I'll show you what we do here. We'll do my PI data block. So this, if you set it up this way, this is the instance data block for another call that we're going to talk later. So it's a little bit confusing going about this way, but this channel has a lot of technology objects, and so it's kind of easy to set up all of the values and everything using the technology interface. And so we'll go through and do this PID compact. It's a super easy, straightforward thing that I've done in the past. So hopefully past Jason can inspire present Jason to be able to set this up on the fly. So general percent, so your controller type, a general PID, and in percent there's no units, and so you can go through and set up different things, and it will go through and set up scaling and scale factors and everything in general. I normally use just a general percent based PID, because I'm going to be sending this value over to my drive in percent. So remember that this value is just getting set in it's just being set in the I just realized, I look over at the screen and realize I had blocked all of the library things because of where my head has been this whole time. We're learning here. But so this is just setting your PID in the processor. It's setting a set point output, and what you send that set point output to changes. It could be a drive, it could be a variable valve, it could be a temperature set point on something else. Like, I mean, it could be anything that's just a value that's going out to something. That could go to a telegram, it could go to an analog output card, it could go to another function block, who knows. So just keep that in mind, that a PID controller in and of itself is just giving you some sort of set point output. So we're going to leave this as general and percent. So this invert control logic is something to, like, the only way, if you're, it is saying if you have a bigger, bigger error signal, you need to have a bigger output, is by default. Inverted means that if you have a bigger error, you need to have a smaller output. So that's what this inversion. So it's going to be making a smaller, like, subtraction. And so, yeah. So we can kind of just go through here and kind of talk about this, but these are just going to be tuning values that we'll be working with later. I want to show you how you actually set this sort of stuff up. Now, I will say, this thing has a tuning, like self-tuning mode on it. So we're going to do this most likely. Our advanced setting, we want to enable our manual entry. And our proportional gain, depending on what we're going to be doing, one might not be appropriate. And we'll talk about what these are here in a second, but I want to show you how to set this up. So remember, this is just the data block that's associated with the PID. These are just the limits and everything on it. We need to call this. And like I said before, with this cyclic interrupt, is we really want to call this at a fixed period of time. And if I remember correctly, there's even a there may even be a thing to where you have to bring in a value for this. It might be on the thing to tell it how often it's being updated, because this is a PID. There's an integral value, so there's a continuing time section on this. So what we're going to do is we are going to create, click the wrong thing. We're going to add a new block. We're going to add one of those cyclic interrupts, and we're going to have our PID cycle. And this is in microseconds. If you notice the S7-1200 was in milliseconds, we're in microseconds because we are on a 1500T. Orders of magnitude different performance levels between the 1500 and the 1200. So let's do this. Let's go 100 milliseconds would be that. Right? So by default, it was that same thing. So 100 milliseconds by default, but this is in microseconds. So 100,000 microseconds is 100 milliseconds, cyclic interrupt, PID. Now, what we're going to do, I believe it is in technology, PID control, compact PID. So PID compact, right? And now we are actually going to select my PID DB. So the data block that was created by the data block that was created by that technology object menu, that's what we're going to select. And we're going to bring this in and yeah. So it is getting, so this PID complex, so apparently in this version of Portal, which is 17, I believe, it has an automatic detection of how often it gets updated. So before there would be an input that you would actually have to tell it how often it's getting updated. So that's cool. Now, if you'll notice, I brought up the extra inputs. You have your set point, your input, and your input in percent. Let's bring up the help file on this just to show kind of like what we have going on. And this can get a little complicated. So let me take the time to go over here to this and clear that. If you're not familiar with these control charts, is there a way I can zoom in? So if you're not familiar with these control charts, these kind of might be a little bit annoying or a little bit confusing, but just know that you're going to be following through, and then this is going to be some operation, and then this is some switch. And so if you have your input in percentage on, it switches between the input in percent versus your input in the standard input. Again, this is a function, and then you're just following through these functions, and then it's going to follow through and then go to your output. So that might have made it worse, but just know that in these, you're going to be looking at, what is this? Who knows? You don't really need to know. It's a black box. You don't have control over it. Your percentage in, your input coming in. So this is some sort of scaling that you're going to be using. So we're going to go, our set point is going to be, for example, let's do a flow control, and we have our All right, let's see. Let's do it this way. Let's have a pump that is connected up to a G120 drive. And it's connected up. Okay. And we have our pipe, and we have a sensor here that is pressure on this pipe. And we want to control for pressure. There's a couple of different ways that we could do this. We can send our set point signal. Our set point is going to be the set point for this. So we want what we want to actually control is pressure. And we kind of go through here. Set point is pressure, and then you need some sort of feedback. So this actually is the feedback signal. So this is going to come back into our PLC. This. And that is actually going to be our, where is it? Invert control, disturbance. So our actual input is going to be this input. So here's how to think about this, because both of these values, both input and set point, this is essentially our feedback, and it's going to generate generate an error signal that is going to send us an output that is going to be higher or lower. And so our output percent is going to be what is going to actually be going to the drive. And if you do everything in percent, it just makes a lot more sense. So what we're going to do is, if this is like a 0 to 100 PSI gauge, we're going to take and scale 0 to 100 to 0 to 100%. Now, it just so happens if you had a 0 to 100 PSI, it'd be the same numbers, but this might be 0 to 1000 PSI. And so you would want to scale that to 0 to 100%. So if you're doing all of this in percent, then that's what you're wanting to accomplish there. Your drive is going to be 0 to 100%. So the output of this is going to be, the output of it is going to be in percent. So with that said, you're going to bring in 0 to 100% for your set point, which you can absolutely go through and have on your HMI a screen that's like, what's your set point? What's your set point pressure? And it be in PSI. But you're going to need to take this value and scale it. That is terrible. The scale 0 to 100. So you want everything in 0 to 100%. So if your PSI range that your system is like 0 to 50, that needs to be 0 to 100%. And then your analog input needs to be scaled to the same thing, 0 to 100%. And so that's the same thing. And it's kind of hard to think about it, but the PID function is going to level out based on how you're set up. It's going to level things out, and it's going to output something that is going to be an increase or not. So yeah, so it is going to kind of automatically create this signal that takes care of the in between. So you don't have to worry about what drive speed scales to the percent that my PSI is. As long as you have everything set to percentages, then it's going to handle it. Because if a drive speed of, say, 10%, so if a drive speed of I'm going to clear all of this. So if a drive set point of 10% generates, say, 2 psi, and the same set point at 50% generates 5, and then 75 generates 10, and 100 generates 30, and you set a input set point, so like a PSI set point scaled to percent of, if your range is, I mean, it's nice to know, because I'm in this setup, if you know your PSI range is 0 to 30 for your machine, and you put in, I want 30, or I want 20 PSI as a set point, it's going to convert that to whatever that is, 80%, whatever it is. And your scaling from your analog input will come back, and as long as these values, so as long as these values are scaled the same, so undo that. So as long as your input and set point are scaled to the same, then you're going to be all right, because inside everything else will scale to what it needs to be. So yeah, it's kind of hard to explain until you actually start working with it, that you're, because when you first start thinking about it, you're like, oh, how do all of these figures relate together? But there is some relation, and the PID function itself is going to ramp up and bring, if you have a set point of 20 psi, if like your 20 psi set point equates to 80%, and your feedback is going to be on that same psi, 80 psi equals 80% on your feedback, then it doesn't matter what the actual output is. It doesn't have to be 80% on the output, if that makes sense. And maybe I'm overthinking about it. It always confused me when I first started working with PIDs, like how, so yeah, so at 80%, you're going to have, so I'm looking at a Simeon. Apologize if I didn't pronounce your name right there, but what, yeah, if 8 volts at output, yeah, if it's in 0 to 10 volts, right, so right, that's exactly going to be right. So your input, if you're like at 80% going into this PID block, your input would be 8 volts going in, sorry, this would be your set point. Would be 88 volts. And so your feedback coming back from your actual sensor needs to be to where scaled to where 8 volts equals 80%. If that makes sense. Even if this sensor is like a 0 to 1000 psi, if your whole system itself, your whole system is only 0 to 30 psi, you need to have on your sensor, you're going to lose a lot of resolution on this sensor, because you're only going to be using 0 to 30 psi, but this sensor is going to be like, if this is a 10 volt sensor, you're going to have 0 to 1000 is 10 volts. So 10 volts, 0 volts. And so if that sensor is that way, you're way down here. You're like 30 psi way down here. So you would have to scale this little bitty section is equal 0 to 100%. That might be confusing, but that really goes back to if you can only output 30 psi with your pump, you don't need to be using a 1000 psi rated sensor, because that scale value, you like you don't have any resolution. You have like one tick, and that's really not going to work well with a PID block, because it's going to see the ever so slightest bit of noise in that 1000 volt is going to be like 2 or 3% swings in the feedback. And so this would be a horrible system. Now, if this were a 300 psi, maybe not. Maybe not that big of a problem, because then you're going to be looking at about a third. You still could probably use to maybe find a better sensor there. But now you have this whole range here. You would have 0 to 3 volts instead of 0 to 0.3 volts or 0.03 volts, whatever that would be. So, yeah, sorry for rambling on this. The first time I started doing a PID by myself, it didn't quite make sense, and I'm sure that I've just confused you even further. But if you have questions, like, and you're watching this on demand, to explain something that's kind of going on here, feel free to ask. Like, absolutely love working through these with you guys too. So in this case, let's have our set point is going to be, let's say it's something from, I probably need to actually move over to the correct, like this. Yeah. So this is going to be our tag that is our PSI and I don't quite have it yet. So, and then let's look. So if we use input in percent, it's going to have a scaling in it. So let's look at the technology object, see how that is. I want to show you how this stuff kind of ties together. So remember this kind of little block down here, it's shown a little bit here. This has a lot more information on it, but you can see that percent is going to be from analog because you're going to need to have some sort of value. So process value scaling. Yeah, there we go. So if you have that input in percent enabled, it needs to go into this, and you can set, say we're looking at PSI and your set point is in PSI. You're going to have your high process value. Let's look at our example of, let's say we have a 0 to 300. So 0 to 300 is our PSI. So this, say this is PSI. And so 0 to 100 is 0 to 300 PSI. But that's the whole range of the sensor. And so if we had 1,000 like that, that would be that. And this is why I tend to just try to bring everything in as percent on the inside, because I don't always like it, because I like just bringing in two values that are the same, like we told. This has this like built-in stuff, but I would have to go through and actually fiddle around with it to see what the outputs came up with. One of the things you always want to make sure that you test your code specifically for your system with your specific sensors. So that's what these two are. And honestly, so because we should have in our we have these two values here. I'm gonna say follower 2. We have this hooked up to a, I was thinking about a way to actually set this up. I mean, honestly, this output here, that if we set up everything as percent, scaled, and then our output is going to be in it. All right. Obviously, we don't have these tags right now. Trying to just get through a couple of things. The biggest thing that you need to know is that this has to be called over and over and over again. You could do it in OB1. The problem is that it's trying to detect the cycle in between. So like your input versus your integral component has to do with how long you've had an error present. So your integral component grows based on how long you have had an error. And so let's bring up just a little bit about a way to tune this now, because that's the basic setup that we have here. Let me get just a blank pad down here on my drawing pad. Just trying to set up some paint here. If y'all have any questions about these inputs, I mean, if you've never used a PID before, I've got a let's see if I got it here. No, I don't have it, but so I guess I got a really early start in automation because of really my dad did this. My dad did this for years. He retired from coal mining after 38 years. This was probably 6 or 7 years ago that he retired, but he also had would do this type of work on the side for like different types of companies. And so I got this kind of experience early on from my dad. And one of the things that he has done is he has written a series of books that we have edited and gotten together, and one of the sections that in one of the books that has not quite been published yet is about PID tuning, and it goes into, I know Lucid was talking about all these fancy methods and everything. It goes into very in depth of different ways and different kind of practical ways of doing this, and I'll talk about those books more once we actually get them out. Right now we only have the AC Drives book out, but I've got a copy of it right here. Hold on, let me see. So we've got our book that we've put together that has all sorts of like topics about these motor basics, and like here's how a VFD speed curve like affects, you can't really see it, affects the torque curve of the motor, all sorts of stuff. So Lucid, if y'all haven't figured out, is one of my customers back in Tuscaloosa, and so he's very aware of this book. This is the first book of, I think we have 6 that we're going to be putting out, and very practical, very combination of, if it's your first time going into these automation topics, you can kind of read through and it's kind of a just conversational tone to it. But then if you know these topics, there's some really in-depth things about, I mean, all sorts of stuff. And then there's also some imaginary, how does he call them? He calls it imaginary customer experiences. Or like definitely not stuff that he's gone through in some of his experience, but definitely stuff he has, like that sort of stuff. Like in working at 38 years in the industry, he has that, and I'll be doing more about those, but just kind of introduce those. There's a section in one of the other ones about PIDs that really goes into more of this, but this just simple topic. So this Motor and Drives is available on Amazon, and it's Applied AC Motors and Drives, and I'll put a link to it in the description of the live stream. But yeah, absolutely, we could do that. And when I get all the other ones up, I'll talk more about that and include those links on that Amazon self-publishing page. So those are available. And so put this up. But let's talk about PIDs for a minute, and kind of like the different types of functions that are going on with PIDs. So is it over here? There? Yes, it is. So ultimately what a PID function is you want say, I normally talk a lot about drive functionality, and so you end up like speed, or like a speed set point or a position set point, but you can also have a pressure set point, a flow rate set point, volume, anything that like you want to control. Is there a good way to freeze output? I believe I think there is. I thought that there was a way to freeze the function. So Lucid asked if there's a way to freeze the output of the function. If you're wanting that, hold on, let me just see something real quick. So let's go to the actual data block for this. My PID, and then just open, not that. Open DB editor. So this is the actual, if I actually have the right screen pulled up. Ta-da! By the way, I'll show you. So if you right click on the technology objects, remember technology objects are really just data blocks. Right click, open DB editor right there. That brings up the actual data block for this. And I want to say there's a freeze output. Really thought that there was a freeze output on this. I know there was a freeze output on the old version, the version that is for the 300 and 400, which it's a little bit more obnoxious. It's not quite as, it doesn't have as many features just in terms of the auto update detection. So how this block knows how fast it's is detecting the updates. Or I'll have to come back to you on that one, Lucid, because I thought there was, and I thought it was kind of dug down into this. Hold up, let me look at something, because it might be in this mode. The mode value. Because I want to say there is one. Maybe not. I'll have to come back to you on that one, just in the block. Oh yeah, definitely flipping it to manual mode and then sending it. Sure, yeah, Steve. I mean, you could always do something like this. Yeah. Yeah, you could always do something like this, like a move. I don't know if I'll actually be able to do this. Let me just define some tags here. Oh. Don't ever. I hate even showing this on the screen, on the stream. Yeah, so the manual modes forces it to whatever your input is, forces it onto the output. So like your input, like your scale percentage would be the output. And so you could do something like this to where you're moving like a and I hate doing this. I'm going to deleting all of these, all this in memory. But yeah, so we're moving this drive set point. We can move this drive set point into the frozen set point, and then like you can do like a you do like a if freeze set point, then you can can like swap this back. You know, like you could do like an update. Yes, Lucid. Yes, in memory. Bad. Ugly. Go away. Ugh, ugh. But I'm just trying to make it to where I can have some tags. Don't shame me on stream. But yeah, then you could have like a drive frozen set point to where you're actually disconnecting this output, and kind of doing some shenanigans with the output. Like that may be the best way to do that. The only problem with doing it kind of this way would be with your drive set point going out. Then if you unfreeze it, you could have a pretty wild, like wound up set point in your PID controller. So it could go crazy. So that's just kind of like stepping in and going from there. Yeah, you would definitely want to restart the PID, and that's part of the things. Like you would on that. Yeah, honestly, you'd probably want to. Yeah. I want to say that there's a good way of doing that. I mean, you could throw like that drive set point. You could throw the drive set point in as the scaled feet or as the input, or sorry, as the set point, and then just flip it to manual mode. You could do that sort of shenanigans, because then that way you're not going to be spooling up. You're going to be spooling up your PID function, and then when you switch it back over, that probably is the best way to do it. The only problem is you have a disconnect between the drive percent set point, or drive, yeah, so like the drive set point and your actual process value set point. And so yeah. Yeah, there's that. So let's talk real quick about this. I'm going through deleting all these in memory afterwards. We shall not have in memory in our program. If you're new to Siemens programming, don't worry. Like we're just being gatekeepers. You can use in memory. You'll just be judged. It works. It just makes it really hard to troubleshoot and like organize, and like it just, us old people, like that's why we do it. I will say the fact that like I was just going through and defining tag. If you've only ever used like Alan Bradley, that's how we know that you're an Alan Bradley programmer, is you go in and like you type in something, you just type define tag, and then all of your inputs and all of your programs in memory. And so, but yeah, we want you to come over. We want you to so we're not going to make fun of you. We just know we know. But yeah, so topics, PIDs. Thank you for getting me off topic, Lucid. Your sketchpad. We're talking about PIDs. I have this like thing where I was going to sing a song about PIDs and torture everyone, but it's not gonna happen. I'm not that guy. I don't need the income. I won't do anything for it. So let's talk about PIDs. Let's talk about UC. All right, so PIDs. So this one, let's say this is stay with our PSI on our, and then this is time, as always, because time marches on. And let's have a value in red, which is our set point. And so we go from 0. Let's just say this is like 0 to, let's make it something that's not, well, no, let's just do it like this, 0 to 100. And then time doesn't really matter what the scale is on it. So we go from 0 and we set a set point of, let's say 30 PSI. Like this. Okay. And then we want to change our set point again to, say, 50 PSI. Ooh, yay, wavy. Your set point shouldn't be wavy. If it is, you're in trouble. But our set point's wavy. I drew it. So, any real system cannot respond instantly. Our set point can, and so any real system cannot respond instantly. Just physics or something, like has mass, I don't know, some conservation of energy and momentum, or I don't know. But so we have our pressure, and we want our pressure to go up pretty quick and then settle out. Right? This would be a crazy awesome system. Right? It just, that'd be a really well-tuned system. But that's not how things happen in the real world. Most of the time, it'll be sitting here, and we'll have overshoot, and it'll look something like this. And that might be more realistic to some of our systems. And if you work with PIDs, you kind of understand the heartache of this. But some terms. What's up, Adam? How's it going? We are talking about some PID functions right now. We've gone all around the world today, and we're closing up just with a little talk about the concepts of tuning, the gut feeling tuning. Lucid brought up some fancy tuning techniques that we might go into, but not today. We're going to talk about just kind of gut feeling. So this area, what's a good color? Brown. This area is called overshoot. And this is really basic stuff. Overshoot is however much your actual process overshoots your set point. And if you have, there can be a way that this value has what's called there's a fixed error. It's called a steady state error. And so sometimes you can make a change and your value will respond like this. And this little gap here, that's your steady state error. Okay. And if everything were perfect in a system, you want things to come to as close to your set point as possible, as quickly as possible, right? So really, we just want our set point, or sorry, our actual system to be as close to our system as possible, or our set point as possible. In this last case over here, in this last case over here, it's never actually going to reach our set point. And it has this pretty big overshoot. So that's probably not what we want to do. Well, in this system, it has this ringing that's like constantly gonna ring. And in a drive system, if you have this sort of thing, that will make noise. I mean, you'll hear that noise. And if you ever get your gain too high, and we're going to talk about gain, so P gain, integral gain, and we don't talk about derivative gain because it's not used nearly as much. But your proportional gain and your integral gain are the two things that you really need to do. So proportional gain is how fast you react to kind of this overshoot sort of thing. How fast your difference is between what your set point is and your actual value. So this is taking your actual value and multiplying it just straight up by a number in order to come back to the set point. So in this case, this would be a negative value, negative something. And then this would be a positive because it's trying to get up. So if you get, this is essentially like taking and multiplying by your error. What do I mean by error? Your error is you have your set point minus actual equals your error. Okay. I spell good. So your P gain is just straight up P times error. Okay. So if here, this would be a negative error. So it'd be coming down. This needs to come up. Okay. So actual minus set point. You want to get it coming down. This is plus, going that way. So I guess probably set point minus actual, if I could actually set point minus actual, negative, positive, negative, positive. Anyway, so that's what your P gain value. So if you have a big overshoot, this is going to be a really big number. So percent wise on the output, this is going to be outputting something that's like, if P gain is high, your error or your correction is going to be really high. And this can change really fast depending on how fast you're updating your controller. It can change really quick. So this came up really fast and overshot. So this P gain value up here is going, if this is over 1, then it can get really high really quick. And what can happen if you get your P gain too high is it says, it's like saying, oh crap, I really have a really big difference. So that means, say my P gain's 10, and this is a 30% difference. So that's going to be a 300% output. That's a lot. And so anyway, that's going to go, pew, it shoot up. Well, the second it goes right here, it's going to go, oh crap, I need a negative. Chew, it go down. And so you get this like roller coaster of instability. So all my So you'll get what's called, I'm saying ringing, like a ringing in your ears, because that's literally what it does. It's like a tuning fork, and it like will actually do it. If you turn on like a drive system, on like a S120 drive system, it's always, so when we would do these little training, the actual training demo unit cases at like in Siemens training centers, they don't have a lot of inertia on the little wheels. And so you would do the automatic tuning, and it would tune them way too high. Like the P gain would be crazy high. And so you would always know the guys that it was the first time messing with that function, because they would just leave the value, the P gain value in it. And the second that they go to start it, it just makes this horrible noise. And it's like, and it sounds like a tuning fork, like a really high pitched like whistle. And if you're a drives person, you've heard it. Everyone's heard it. The first time I did it, and I learned it. And so it's just funny that that comes from a P gain that's too high. So your proportional gain is too high. Well, if you get your proportional gain too low, I'm going to clear off all of that. You get your proportional gain too low, you might get something that is really slow and never actually gets to the set point, because as it gets slower, or sorry, as it gets closer, the gain gets a little lower, and may never actually reach it. And the thing about it is, a simple proportional controller can never actually settle onto a set point. You can never have zero steady state error with just a proportional controller, because there has to be some sort of dampening. I say never. If you say never, you're always wrong. Think about that for a second. There are very few mechanical, like you would have to have some sort of mechanical system that would dampen this thing, like a shock absorber. So a shock absorber, like a strut, like on your car, the spring is a proportional, and the a proportional controller, so it's controlling position. The further you get away, the harder that spring's going to push, and the actual shock, so the hydraulic, is actually the integral gain, because the faster you move, I guess that's actually derivative, but the faster you move, it's going to change. But that's some sort of dampening. So if you have dampening in your mechanical system that you will dampen out a system, then technically, I guess, a proportional controller could work. But most of the time, you're going to end up with a situation like this, to where you either don't have enough gain. So this is under, and this is so this is under damped. So this is over damped, and this is under damped. Actually, this is under damped. But we'll go out, say, so if you don't have enough gain, you're gonna get something like this. If you have too much gain, you're gonna get something like that. And if you have too much gain, this can actually get, and you hit resonance in the mechanical system, and it'll go boom, destruction. And this is not what you want. You don't want to get mechanical resonance. You don't want to get, so be very careful when you are working with your P gain. When you start off, lower is better. Always. Okay? You want to have the lowest P gain that you can get without having undershoot, or this situation to where you have an overdamp situation where you're never able to get up. Because some systems, this might actually be okay. This this, like it might be okay for your process to take a few seconds or maybe even a minute to like reach its value, like an HVAC system, for example. Temperature in a room, not going to react quickly. So having a little bit of P gain, like an overdamp system like this, might be all right. High P gains will almost always cause problems. Like you're going to be oscillating. So with just a P gain, you always have this steady state error though. Well, that's why you need the integral portion of the PI controller. So the integral portion takes, and if you have, it takes, and judging by the name, you would hope that it would have to do something with an integral. But so it's taking how much error there has been over a specific amount of time. And if you've done calculus, that's going to be, so like in this case, like if this is T 10 seconds and this is 10.5, this would be from 10 to 10.5 of FP of your function. So that's what, like if this is f of t, your actual response curve, that's what this is. Okay, that's why it's integral. Get all that crap off there. Calculus is scary. But you don't really need to know that. You just need to know that you're taking a time slice and looking at the error during that time slice. And the way Siemens does its kind of functions, because there's two ways to think about this. It's how much error is accumulated in your time. So like in your integral, these guys, like your actual ranges, or it's how long of a time are you giving it to correct for the error underneath here. So, and the latter is the way this is. So the way that you think about the PID functions, because you are in seconds, milliseconds, that's the time frame. You have an integral time. So the value on this actual block for the integral is a time. And so this is in seconds, milliseconds, whatever. So the way that you could think about a Siemens PID for the integral portion is the higher the time, the less it actually does. So in this, there's the default value is like 20 seconds. So if there is an error, it is going to be taking 20 seconds. How much would it take for 20 seconds to correct for this, if that was a steady state error, it's correcting it over 20 seconds. That's nothing at all. Like that's no operation. That would be something. 20 seconds is a very small operation. So 20 seconds takes a really long time to correct for it. So as you lower this down, say 1 second, that is a medium, like reasonable time. It depends on your how fast things can react. In a drive system, this is an eternity. You might as well not even have any integral on a drive. So you're talking hundreds of milliseconds on a drive system, tens of milliseconds that you're wanting on a drive system. On a pump system, a second might be a reasonable time. I think I have some pump systems that have like a 1.5, 2-second integral times on it, because you don't want it trying to come down too fast, because if you have a low p value and then your integral is operating more than your proportional, you can kind of run into some problems. So practically, let's look at ways to do this. So we're going to clear this, and I'm going to do this. Select. Oh, I have to make it a cursor. Select. And then I'm going to select all of this stuff. Select. What you got, Lucid? That's going to delete. Just whatever. Do control. What you got? What if I have a process that I just want to correct every couple of minutes? Yeah, it is useful. Not really. Not really. In that case, you would want to turn on and off your PID. Like if you're wanting to like correct that that process value, like you're okay with letting it kind of like float up to a limit, and then you want to correct it back up to a limit. Yeah, that's a case where you're wanting to turn on and off a PID. You don't want a PID continually doing that, because your integral times are going to be really long, and it'll never be able to actually operate quickly. And so that would be kind of, think of it as having your air conditioner running all the time. Your air conditioner running all the time, or it turning on and off at certain set points. That is actually called, there is a specific type of PID controller that has it's called a deadband controller in that. So let's talk about that. Way to distract me. You're good with that. No, but this is good. So a deadband controller would be like if you have your value here and here's your set point. And you want to set, let's say, a deadband around your set point of plus or minus 5%. So that's what it is. And you have your PID controller working, and it comes up and it comes in, and based on the gain, it kind of gets in here, and anywhere inside this deadband, it's okay with whatever it is. And so this would be like something that has so it'd come up, and if it was shot out, it would bring it back in, and as long as it never went back out, it might look like this, or the system might be stable at something like that. It may look like that. That's called a deadband controller. And I know my southern accent is not easily interpreted by everyone, but that's a deadband controller there. And that can simply be taking a PID and then turning it on and off. And so that's probably the best way that you would want to do it. Or it sounds like you might not even want a deadband. You might just want to run it for like 3 minutes and then have a correction. And so like you want it to correct up and then just run at that set point, and then after every 5 minutes turn the PID controller on again. Like that's probably what you're wanting to do. So let's do this. Does that kind of answer your question, Lucid? Cool. Okay. I love how the music got really serious when you're talking about deadband controllers. I really hope y'all can hear the music, because otherwise I just sound crazy talking about the music. I promise you there's music going on. Awesome. So let's go back to this. So we have a set point. And this is called a step input. and we'll talk about the difference between like step inputs and ramp inputs, because PID controllers act differently. They act differently based on them. But what you would want to do is set up to tune a PID. The first thing you want to do is kind of get your baseline step. And so this is called a step input because it looks like a step. You're down here at something, you step up, and then you let it sit. And this doesn't always have to start at 0, by the way. In fact, most pump systems, you don't want to start at 0, because that whole exponential version or stuff with a pump, you have to be running a pump at some sort of minimum speed, say like 33% or whatever it is, in order to actually be able to generate anything. So you don't want to start at 0. You want to start at some value. You want to have a little bit of pressure there. All that to say, every system is different, but this is in general. You want to generate some sort of step input, because this is going to kind of be, for most systems, this is going to be the hardest to react to. And this is, you just go from 0 to 100, 100 to 200, whatever it is. And what you want, so you want to take to start off with, you want your P gain to be, and this is for Siemens. So Siemens PID. Just the way Siemens does their, because integral can be interpreted a couple of different ways. So, and I'm not familiar with other ways, but you want your P gain to be low, your I to be high, and your D, your derivative, you normally don't use a derivative that much unless you have highly dynamic systems. So we don't even really use that a lot, but there are reasons to. But we're only going to talk about PI right now. So so you want to start off with your P gain lower than you think would be reasonable. So remember, 1 is whatever the difference is in your values. So think about if your difference in your step is, say, like 10. So 10 in your set point, 10 PSI, 10% of your overall PSI. How is that going to react to, how are you going to react to that on the actual process? So is a 10 PSI step, if you have an P gain of 1, that means it is going to output 10% for that. So so that difference is going to be that 10%. Would you ever think about a 10%? Is that enough? So a lot of times on like pump systems and stuff, this is going to be less than 1. So I want it to actually be like 0.5. something, because I want to I would much rather it be softer than too hard. So like I would much rather the P gain be lower than too high, and I blow out seals or break something or like accelerate something, throw something across the room. Like I would rather the P gain be very low. And you want to set up this trace and then test it just to see how your system's going to react. And so your integral gain is going to be high. In, like I said before, default is 20 seconds. So 20 seconds is normally incredibly high for any sort of system that, other than like an HVAC system or like a oven system. So anything that has something real, like physical, that you're moving around, 20 seconds is going to be high enough. And you're going to want to trace the response. So you're going to trace your feedback signal, and you're going to make this change and you're going to trace it. And hopefully it kind of looks like this. Or, I mean, it probably won't look like this. It'll probably look something like that. So let's undo this, undo that. It's probably going to look something like this. And so after that, you want to slowly increase your gain so that this starts to go up like this. Eventually, you will increase your gain to where it overshoots, which is good. You want to slowly increase it to where it overshoots, and then we'll come down and kind of do this. And in general, as long as you're doing this in slow steps and you're not increasing by like 100%, like doubling your P gain input every time, then you in general want to try to find the P gain value to where it begins to oscillate in the steady state. Okay? So you want to find that value to where steady state, you're not slowly getting smaller, to where, and obviously this might not be appropriate for your system. And so if you have something that can't take this sort of oscillation, the second you get a little bit of overshoot, you're probably good enough. Like if you have some sort of system that can't handle any oscillation, then yeah. But in theory, you want to find the point to where it starts to oscillate, because that's going to be your maximum gain value that you ever want to limit it to. And so that's kind of the kind of metric that you're wanting to do. You're wanting to set the highest gain, that you want to set the lowest gain possible to achieve a quick rate. And normally that's go up, find the highest that you feel comfortable with, and then back it off to where, because your gain, this overshoot will shoot over, and you'll notice where this first crosses is here, and then it kind of settles out down here for this line. Well, for this one, it first crosses a lot quicker, and if you get it too high, it never settles out. But if you find that kind of that medium, it will actually settle out a lot. It'll settle out a lot quicker with a higher overshoot. The overshoot's higher, but you settle a lot quicker. So this would be like the settling time quicker. So here's a couple of things, a couple of warnings about this though. this overshoot might destroy your system. Like, so again, you want to have this as low as possible to get the performance, but you want to push it high until you find the limit for your system. This overshoot might blow valves out. It might damage stuff. So there might be a theoretical quicker settling time, but it destroys your system, and guess what? You're out of job. But so you don't want that. So always go slow. Be afraid. Respect, and I know that sounds like a joke, but like, the more you are around automation, the more respect you have for potential mistakes. When you first start out, especially if you start out from kind of a software programming background, you don't quite understand the impact of a mistake. This at worst could damage this could damage a machine, but at worst it could actually kill somebody. And so PID controllers, go slow. Not to be doom and gloom, but once you have, that's a lot of stuff. I'm gonna have to do this. So once you have a Control A, delete, brush, back. Once you have a step that has a fairly quick but safe overshoot and settling time, that's when you want to start lowering your integral, because essentially what it is going to do. So remember, when you start lowering the time value on that integral, it's actually increasing the effect. And so what will happen on that is you can think it will start to, the overshoot will probably be close to the same. That was terrible. The overshoot will probably be about the same, but what you'll see is your settling time will start to get tighter. And so essentially it kind of pulls this back. So slowly, this will start to come down, and your overall settling time will start to get less and less. Now, you can get to a point to where if this gets down too low, you'll get instability with it as well. So integral needs to be as the integral you want to be as it's kind of the opposite. You want it to be as high as possible, so like the largest time, while that's not your Discord, it's my Discord. You want it as high as you can get it, while keeping the settling time low. So remember, it's going to essentially take these peaks, because this is kind of a product of your peak gain, is how fast those peaks happen, and it's going to tighten them up. The way to think about it, I'm going to move them that way. And you think, okay, well, I just want a 0. No. Well, in a Siemens controller, if you put a 0 in, it disables it, because that would be like an infinite. You would be dividing by 0. So we're not going to do that. But anyway, so these are kind of the basic principles, and that's kind of the gut feeling approach, which the science there are, and we may talk about those and we'll go through those, and when we get those books published also I will do that. But this is kind of the 2 points of a 2 points of the PI controller, and it's really, you're trying to slowly make changes, slowly move up the performance of everything, and kind of go from there. And yeah, so we've kind of gone a little bit longer, and it's probably because I wasn't quite as fluid with everything today. So I really appreciate everybody that's come on this. There's a lot of different things that you could do with these, a lot of different applications. If you have a specific application that you would like, drop it in the comment, or would like for me to talk about, drop a comment on the on demand, and I will try to bring it in the next live stream. I will probably be at least 2 weeks. Yeah. Next week, I'm going to be on the road, so won't have a live stream next week. Hopefully you have some time off for the holiday season, and you get to spend time with all of the people that you want, or the cats that you want in this case. Yeah. So with all that said, I'm so thankful for the community that's growing so far. Again, remember, liking this, subscribing, and commenting are the 3 biggest ways to get this out to more people. And the more people we have, the more questions we have, the more interaction we have, the less you have of me just droning on about some random thing. So yeah, see, Merry Christmas to you guys. And I'll see you probably in 2 weeks live. But I might drop a couple of edited videos either from this. I've got the start of a fun edited video that my wife is waiting for me to finish the actual screen capture. I have all the fun stuff done, having a little bit of fun, trying to make it not just technical content. But anyway, we are gonna end the broadcast now, and glad you came, and I hope you come to the next one. And remember, hit the notification bell so that you get notifications, so that when I go live next time, you can join us. But yeah, until then, Merry Christmas, Happy Holidays, and we'll see you.